and I leave the stage to the Professoressa Ploteghe to introduce the next speaker and continue to enjoying the fnip webinar.
Thank you, Andrea. It's really a pleasure to have our last speaker here, Professor Erhart. So maybe while I give a brief introduction about him, he can start sharing the slides so we see if everything works. So Professor Erhart is a professor in condensed matter and material theory division at the Department of Physics at the Chalmers University of Technology in Sweden. He got his PhD in material science from Technische Universität in Darmstadt in 2006. And then he moved to California to the Lawrence Livermore National Laboratory, first as a postdoc and then as a staff scientist. And then he came back from sunny California to Chalmers in Europe in 2011. In Chalmers, he leads the computational materials group, and his research focuses on the atomic and electronic scale modeling of real materials, with emphasis on interatomic potential and machine learning methods. And today he will talk about modeling Raman and infrared spectra of very interesting and different materials. So Professor Erhart, the stage is yours. And thanks again for accepting our invitation.
Thank you very much. Can you hear me? Yes. Okay. And I think you can also see my screen, right? Okay.
Yes.
Thank you very much for the sum of our work. I did not exactly know what to expect in terms of the audience, so I prepared a relatively, what's the word? Relatively, there's complexity at different levels. So let's see how this goes. First of all, what you see here is actually the archipelago outside of Gothenburg. So this is not how it looks like right now, but you mentioned coming back from California to Europe. I can also recommend visiting the Swedish West Coast. So if you have the opportunity. So as you might have seen the title. So basically what I want to talk about is Raman and infrared spectroscopy, and specifically how one can predict such spectra from ML-MD. So what is ML? ML is machine learning and MD is molecular dynamics. And what this allows us to do is to treat materials that have strong levels of anomalisticity, that are disordered and defective materials. So if you're not coming from the materials area, what those terms mean is basically materials that are not described by conventional approaches. Materials that have very large, that require very large supercells to be described, and or have many different components, and or have large degree of anomalisticity. And anomalisticity would basically mean that the bonds between the atoms are very soft. So to illustrate the basic principle, I show you here the infrared spectrum of water. And water is actually a material that is obviously very important, or a substance that is very important. It is also one of the most complex substances that we have. I mean, given the fact that there's only two components and its natural abundance, it's absolutely flabbergasting how complicated this material is. So what you see here looks rather innocent. There are 1, 2, 3, 4, 5 features basically that you can distinguish. And with quite a lot of work, people have been able to figure out what those different features correspond to. So if we start over here in the wave number range of about 3,400, 3,500, this corresponds to what is called an OH stretch, right? So this is basically what you see here on top. This is a water molecule. And you can see that in this case, one of the two hydrogen atoms is moving relative to the oxygen. And in terms of the harmonic oscillator model, the smaller the mass, the effective mass, the higher the frequency. And this is involving the motion of hydrogen. And this is why this is the highest frequency band. This is actually, in terms of IR, a rather broad band. And I'll explain in a bit where this broadness comes from. If we then move down one bit, then you see that the feature at about 1800 inverse centimeters corresponds to bonding. This is a mode where the two are vibrating against each other. And then becomes a bit more interesting, actually. About 800 or so inverse centimeters, we have what is called a libration mode. These libration modes are, I illustrate this here with just a single molecule, and it looks like the molecule is just rotating. But you have to imagine that this molecule is now in an environment of other water molecules, and these other water molecules hinder this motion. And so this kind of libration motion looks more like a soft wagging, right? You go basically going back and forth because you're restricted in your motion. And then the lowmost frequency here, this is at barely 100 inverse centimeters. This is what is called an H-bond stretch. So these are, now we're talking about modes that involve multiple such molecules. And this is a hydrogen bond that connects two of these molecules. So this is the kind of information that you would find in a typical infrared and, as you'll see in a moment, also Raman spectrum. Now, this is over superimposed on this first spectrum, the IR spectrum, which was the blue line. You also see now Raman, and Raman, you see that you pick up similar features, but the overall weighting of these different features is different, and that is because Raman and IR pick up different types of excitations in your material. The way in which these kind of spectra are usually obtained, I mean, so experimentally you can determine such spectra. What is always hard is to figure out to which extent we can understand the features. In chemistry, it is not unusual that you use IR to do structure identification or to identify different types of molecules. But there's a lot more information in these, and for that purpose, it is very useful to be able to predict them from a description of our material that is rooted in quantum mechanics. So what you, as a very simple illustration, I show acetone. Acetone is this molecule here. It is one of the simplest organic molecules you can imagine. And the blue line, this is a theoretical prediction. This is based on density functional theory. And the orange line is an experiment. And you see that overall, while some of the lines are maybe a bit off and some of the frequencies are not correctly described, the overall structure of the spectrum is actually reasonably reproduced. The remaining features or the remaining errors, the ones that you see over here, for instance, this basically indicates that there are certain modes that the theory describes as too stiff, and you can even see that this is rather systematic. So even this one, this very pronounced feature is what you call, this is a situation in the gas, right? And so this is why I emphasized in the experiment that this is done for very dilute conditions. These kind of spectra would be the ones that you're interested in if you are in astronomy and you want to identify such molecules in your observation. The feature here that you see is the most pronounced. This is a CO bond. This is a double bond between the carbon atom that you see here and the oxygen atom. And this is as you can see, this is the most pronounced feature. And this is because IR spectroscopy is sensitive to dipoles. And the CO bond is strongly polarized, and hence has a strong dipole. And this is why this is the most strongly visible feature in the spectrum. If we now compare this to acetone as a liquid, you see that there's a lot of things that change, right? And so this is this gray region here in the background. And without going into the details of why this looks like this in acetone, this just goes to show that if we go from a single molecule to many molecules, then a lot of things change. And this is where basically these kind of conventional approaches, which are computationally very expensive, directly rooted in quantum mechanics, start to struggle. So how can we actually overcome this is one of the questions, right? So if we're talking liquids, we can make the situation even more complicated or complex, and this would be, example here is, this is barium circonate. Barium circonate is a so-called perovskite. This crystal structure is shown here at the bottom. And what makes this system, that barium circonate temperature, is actually cubic. And cubic materials should not exhibit any kind of Raman intensity. Nonetheless, you have very feature-rich and pronounced Raman signal. And this is because what you're seeing here are higher order Raman scattering processes. These are basically multiple different vibrational excitations that combine to form this kind of spectrum. And again, this is something that is actually borderline impossible to predict with an approach that is fully quantum mechanical from the bottom up. This kind of dynamics that you see here in barium circonate via the Raman spectrum is just one example for a type of spectroscopy that you can do in solid state for systems that exhibit interesting dynamics. What you see on the right-hand side is another perovskite. This is cesium-lead iodide, which actually has, and what you see is a so-called quasi-elastic Newton scattering experiment. I don't want to say so much more about that, other than that you can see that this is how these kind of spectra look like, and that if you don't have any kind of modeling support, it is extremely difficult to attribute the source of this kind of deviation that you see here between the red line, this is the perovskite phase of this material, and the blue line, which is a non-perovskite or so-called delta phase. So that's the starting point. And this basically, in a nutshell, we have several challenges to address here. We need to think about how we address solvation effects. We need to think about how we treat anomalicity, the softness of the structure, and temperature, and also higher order scattering. So let's take a step back and think about how infrared and actually also Raman spectroscopy work. This is again this acetone molecule that you saw before, and here I actually, with this red arrow, indicate for you the orientation of this carbon-oxygen bond, which is this really strongly dipole active contribution. If we put our little molecule in free space and we let it do its thing, this CO bond will vibrate. The molecule will also rotate, right? But overall, what is going to happen is that this dipole will change in size and in orientation over time. If I now come in with an electrical field, I can basically do this dipole, I can resonantly excite it. And this is what IR spectroscopy basically does. I pick out all the resonances in the excitation spectrum, all the resonances that I pick out in my system will appear as pronounced features in my IR spectrum. And roughly speaking, we can think of this as a slight change in the color of the light that comes out. So from a fundamental level, if we go back to the physics of this, the infrared spectrum can be written as the Fourier transform of the dipole autocorrelation function. This is spelled out here. So here mu is our dipole, and mu 0 indicates that this is the dipole at time 0. Mu t is the dipole at a certain time later. The epsilon here, or epsilon hat, that is the orientation of our lights, or sorry, polarization of our lights. So we can even include this here. This just makes things a bit more complicated. But I hope you see that what I basically have here is I'm probing the correlation between the dipole at a particular time 0 and another time t, and a time t later, and then I take the Fourier transform of this whole of this correlation function. It turns out that Raman works rather similarly. In that case, instead of probing the Fourier transformation of the dipole, I probe the Fourier transformation of the polarizability. Right? And that is, in a nutshell, the theory for this process. Now we need to ask ourselves, how can we sample these kind of autocorrelation functions, right? So the first thing to notice is we basically have to have a means in which we can propagate our system in time. This means we have a certain position of all the atoms in our material or in our molecule, and we want to propagate that. This is rather easily done using a technique called molecular dynamics that I'll briefly show on the next slide. In order to propagate an MD, we need information about the energy landscape, right? And so that is then the second need. We need to have a model that can describe the energy of our system and correspondingly the forces as a function of the positions. And thirdly, since we're ultimately interested in either dipole or polarizability, we also need models for those. And those are a bit special because these are tensors. I'll be coming back to that in a couple of slides. But already at this point, I want to make a nomenclature distinction that is sometimes a bit messy. So basically, if we're talking about systems that are local, non-extended in space, this would be molecule, then we can talk about a dipole. If we take our system and we make it periodic, we go to solid, or we go to a liquid, a bulk liquid, then the dipole itself is no longer well defined, because basically I can translate my system and change the origin. In that case, what I should be talking about is the polarization of our system. Both the dipole and the polarization are rank 1 tensors. Correspondingly, if I'm thinking about the polarizability, which is a rank 2 tensor, in a solid, this would be the susceptibility. This is just useful to keep in mind. In the remainder of this presentation, I just stick to calling this dipole or polarization mu, and I call the polarizability or the susceptibility alpha, so it's less confusing. So let's look at the first part here, the sampling of the dynamics. So in materials, this computational materials simulation, this is a standard technique. In case you haven't seen this, I illustrate this here with a little movie. What you see is a surface of a metal alloy. This is actually palladium, and this is an alloy with gold, the little yellow bubbles, and then with copper, those are the little orange blobs that you see in between. This surface, if you actually put it out in the environment, will typically be covered by carbon monoxide. And in this particular case, we also added hydrogen because we were interested in hydrogen sensing. I chose this example because it shows you a little bit the complexity of these systems. And so if you run an MD simulation, what you basically do is you are propagating the Newtonian equations of motion in basically just this form, right? So this is a second order differential equation in time, and we just have to integrate this, which we can do numerically. And as a result of this integration, I can evolve my system, in this case, over see how all the atoms vibrate, and some vibrate more and some vibrate less. And this is exactly what we pick up in spectroscopy. So if we have now what we need now in order to do this kind of integration is the force, and the force is what we get from the energy, right? So this is nothing else but the gradient of the energy with respect to the positions. If you go into computational materials, there are a bunch of different methods that are available, and they differ greatly in terms of their accuracy and extent in terms of their computational cost. So this is shown in this kind of sketch here. On the y-axis, I'm showing you the accuracy of different methods, and on the x-axis, I show you how expensive they are in terms of the system sizes that we can address. So in order to do these kind of calculations, we usually go to a high-performance computing system and use anywhere between 4 and 400 cores, CPU cores, or nowadays, of course, also increasingly GPUs. I also want to emphasize that these are log scales. So basically here, we would be talking about 1 million atoms, and over here, we're just talking about 10 atoms or so. And without too much ado, there are basically 3 groups of methods that I wanted to show here. If we want something that is extremely accurate, we have to do beyond Hartree-Fock type of methods. If you're a chemist, you might know about configuration interaction or multi-reference type of methods. This is this kind of category. These are extremely accurate and extraordinarily expensive. We can nowadays, even nowadays, only do a couple 10 atoms. This has to do with the scaling, and there's little, and basically there's a fundamental limit to this. In this intermediate region, we have density functional theory, or DFT, which is a workhorse for lots of materials and one of the main consumers of computer time at HPC centers around the world. And up here, we have empirical potentials, right? Now, where we want to be is here in the lower left corner. This is what you would call, this line here is what you would call a Pareto front. You try to be as far in the lower left corner as you can. You want to be as accurate as possible while paying as little as possible for that. And this is where MLIPs come in. And MLIPs are machine-learned interatomic potentials. So how do they work? Essentially, what we do is we take the total energy and we decompose it in a bunch of individual contributions, right? So this is EI here. And then this EI, we can write in a simple form. We have, based on physical principles, a certain expectation about how atoms interact with each other. For instance, in the case of a pair of atoms, you would assume that the pair potential has this kind of form. In other words, if we come very close, if the atoms come very close to each other, they repel each other. And if they are very far, then they don't interact. Those are these 2 limits. This is repulsion. This is not interacting at all. And in between, there's a region where they basically are bonding to each other. So in an interatomic potential, not machine-learned interatomic potential, just a regular one. What I do is I basically take my atomic positions, I translate this into distances, I pass these distances into this mathematical model that I can write down based on physical principles, and I compute this energy. It's a physically well-founded process, but it is and fast, but it is also not very accurate. Now, what happened over the last 5 to 10 years or so is that machine-learned potentials really came onto the scene, and they really provide a qualitative change with respect to how we can describe these systems. So the basic principle is actually quite similar to a regular interatomic potential. We start with our positions. Now we turn these positions into what we call a descriptor. This is just a way, typically a vector, that describes the environment of each atom. And then this descriptor vector is passed into model. This model can be a neural network, this can be a Gaussian process, or it can be even a linear model. This is rather free. If we then do this, since this has been realized, there's been an explosion of approaches. And without going into detail, basically any technique that you can find in machine learning has been applied to this problem. This includes Gaussian processes, feed-forward neural networks, graph neural networks, linear models, combinations thereof, transformer architectures, and so on. So the particular approach that I will talk about now is NEP. We come back to that in just a moment. So let's get started. First of all, with all these different architectures being around, the question is, which of those should you choose? Which of them is actually suitable for the problem at hand? And to show this, here is another type of Pareto plot. This shows you now the mean absolute error of the energy as a function of the compute time. And again, we want to be here in the lower left corner as much as possible. These are all sorts of different architectures that were taken from a recent paper from Leimeroth and others. And this is done for silica, which is just a very convenient test system because it's both complex and still sufficiently well understood also experimentally. So if we position our neural evolution potential approach in there, then this is basically sitting here, and this doesn't look yet very impressive. But now comes an important detail. This benchmark was done for 768 atoms. Those are rather small systems for the kind of problems that we're interested in. We would rather be interested in systems that have at least 50, 100,000, or even 1 million times of atoms. And if we consider those, there is a pronounced difference between NEP and other state-of-the-art approaches. And basically, already at 50,000 atoms, NEP clearly dominates the Pareto front for all these models, right? And so this gives us confidence that this approach gives us exactly this kind of balance between performance and speed that we need. So there are some technical details to how, sorry, I wanted to add this. So basically, if to give you a perspective, 10 to the minus 7 here, this corresponds to simulating 1 nanosecond per day with 100,000 atoms, and you can do this on a single GPU. The type of GPU that you use for gaming is perfectly fine, right? So this was done here on I think it's a 4090 or a 3080 second or last generation GPU. So there are some technical aspects, and feel free to ask me about that. I will go over this rather quickly. But essentially what we do, there's a certain approach to how these are trained that makes these models as effective, as efficient as they are. This has in part to do with how we construct the loss function, and this has in part to do with how it is trained. This separal natural evolution strategy, which gives rise to the name, is also is a principled black box optimization algorithm, global optimization algorithm that is very well suited for the problem that we're trying to solve. So how does it perform in practice? This is the silica example that I already mentioned. And what you see here is a sort of parity plot. So this shows you on the y-axis how well the model predicts, and on the x-axis, the target data. And if our model performs perfectly, everything will be here on this blue line. And the blue data is for the energies. And you see that this performs really well. This is a correlation coefficient. It cannot get larger than 1. And so this is an extremely good model. And this also works for the forces. You can then also compute, for instance, energy volume curves, and this shows you in solid lines the model and inference DFT data. This all looks fine, but these are not really specific yet, right? You want to make a real prediction. In this case, this would be a phase diagram. And what you see on the left-hand side is the experimental phase diagram. On the right-hand side, you see this model-based phase diagram, and the two are in very good agreement. The parts where they differ, which is, for instance, here, this phase boundary between quartz and coesite, that can be attributed to the underlying DFT exchange correlation function, which itself is an approximation. So, but now we should come back to this slide. I basically said we want to be able to sample the dynamics, and this is where we use MD. We need energy landscape models. This is where NEP comes in. But what about mu and alpha? So mu and alpha are tensors. And that means that basically they have to transform in a certain way, right? So that means if they describe a shape or they describe a direction, and if I transform, oops, this is supposed to rotate, sorry. So if I rotate my coordinate system, then this this red blob has to rotate alongside. And that is the definition, or this is a characteristic property of a tensor of rank higher than 0. And this is what you typically use. And typically this means that you need a so-called equivariant architecture, right? This is why it says the need for equivariance. So how do we solve that? We realize that basically the NEP model predicts scalars. However, if we take derivatives of this expression, we retrieve vectors, right? For instance, this term here, this is a force-like term, this is a vector, and I can exploit this. I can exploit these derivatives that naturally fulfill all these equivariance conditions to construct emulate or representations for tensorial properties. So this is an example for rank 1 tensor. This is how we build that one. It's basically just a cross product of the force term and this and the bond vector. And this gives us this mu. Just to be clear, this is not the same model that we use for the energy. This is a model that is specific, that is constructed in the same way and is only predicting, for instance, the rank 1 tensor. We can also extend this to rank 2, and if we want to higher rank tensors, in that case, we would get this kind of expression. This looks a lot like an atomic virial, for instance. How does this work, or does this work? The answer in short is yes. What you see here is the relative root mean square error in percent for the validation set of different configurations. So this is a water dimer. This is what is called the Zündel cation. And here we have liquid water. And red is NEP, or TNEP actually, the tensorial NEP. And blue are other architectures. And you see overall the performance is very similar. This line here is a 1% error. This is a 1% error. So these are overall very good models. And why would you choose TNEP if you could use any of the others? Is basically speed. What you see here is the speed measure. And you see that, for instance, compared to this SAGPR, which is a approach that is rather popular, depending on the system size, you are up to 2.5 or so orders of magnitude faster using TNEP. And this means that we can evaluate this in parallel to our energy model and basically predict an IR or a Raman spectrum with a minimal computation overhead from an already running MD simulation. To show that this actually also works, for the actual spectra, I show you here this infrared spectrum of water that we looked at in the beginning. And you realize, and you recognize now all the features, right? This is the OH stretch. Over here, we have the bending mode. This is the librational band. And over here, we have the hydrogen stretch mode. And we can discuss this in more detail, but here you have the experimental data. And the fact that, for instance, this feature comes out is a very good test for the quality of this model. This also extends to Raman. No news here, basically just this works really well. Now, how about solid state systems? Here's this barium circonate example again that I already mentioned in the beginning, and you see here comparison between experiment in gray and the NEP model in red. You see a very slight redshift of the spectrum. This is because the underlying DFT functional is slightly too soft, but all the intensities are coming out right. And we can now actually go in, and I don't want to discuss this here, but what we can do now is we can actually decompose the spectrum and tell you where some of these modes are coming from. Since these are higher order modes, this means that, for instance, you would have two different types of phonons, two different type of vibration interactions coupling to each other either additively or subtractively. You can also have higher harmonics and so on, all of which comes into the spectrum. Having this, we can now play with pressure as one example. For instance, we can there's a phase transition in the system between cubic and tetragonal, and as you approach this phase transition, you expect a resonant behavior in a Raman intensity, and this is exactly what happens, right? You can see here at this point here the transition from the cubic to the tetragonal phase driven through by basically just running parallel to this 300 Kelvin isotherm here, and at this point, you go from a second order to a first order Raman spectrum. All of this comes out from this analysis. This brings me almost to the end. So what you see now here, all of this was done with a lot of software development. The packages that are really important here to mention are Calorine, sorry, I should start up here, is GPMD. GPMD is a package that is developed largely by Jiang Fan, who is a very close collaborator, and we contribute to this package. This is all fully documented. There is an extensive homepage. The API is present and all these kind of things. This package is written natively in CUDA. There's a HIP port as well. And this is what is used both for training models and for running them. And then here are packages that are important for actually handling these kind of simulations that are operating from Python. So Calorine is providing all sorts of functionality for driving GPMD simulations and training jobs. And Dinosaur is a package for analyzing correlation functions and mode projection, all these kind of things. If you're interested in this is our homepage, and under the software, on the software page, you will find a lot more information. Very briefly, this is basically how these homepages look like. We spent a lot of effort on maintaining the software, writing software that is maintainable to begin with. So there are lots of tutorials. The APIs are fully documented. We run CI, CD testing, and the whole 9 yards of what you can afford in academia in terms of software engineering. And I invite you to take a closer look at that. So this work involved a lot of different people. The one person I really want to point out is Jiang, who is the main person behind GPMD and with whom this would have been impossible. And this is where I want to end. Basically, what are the takeaways? We can now handle through MD solvents administered in higher order terms. Now, this was always possible, but what really makes a huge difference now is that we can, using machine learning, construct models for both energies and tensors that provide near first principles accuracy with empirical potential speed. And so this is where we can now really start to play. We can go liquids, solids, we can do molecular systems, defects, and so on and so forth. And with that, I'm at the end, and thank you very much for your attention.
Thank you. So thank you very much for the very interesting talk. So if there's questions from the audience, maybe we can start from there. I think this. Well, while people think about what they can ask, if they don't have questions ready, it's probably a naive question because I'm from a biophysics background. So how far are we from possibly predicting Raman spectra and the R spectra of biologically relevant systems? I mean, proteins, or even so there's people that do fingerprints of cells.
This has actually already been. I was thinking about whether I should add that, and then I ran out of time. So if you give me 1 minute, I can even show you the paper, but I can also send later.
That's fine.
Basically, Ethan Berger, who is now a postdoc in our division, he's with another PI. During his PhD, they saw that we had published this technique, and they picked it up together with his supervisor, Hanno-Pekka Komsa, and they took DNA base pairs and made models for DNA base pairs, and then used that to basically predict now let me think. I think they did IR spectra for those. So that has already been done. So if you can then, nothing stops you. You don't have to use a NEP model for sampling. You can use a regular amber, GROMOS, whatever your favorite biomolecular force field is, to generate the trajectory, and then use these kind of models, the TNEP kind of models, to post-process that and get a Raman or IR spectrum out. So in principle, that's
And
not only
yeah, and would it work also for a dishomogeneous sample? I mean, if you have more dishomogeneous sample with more complex composition.
Yeah, when you mean what do you mean with more inhomogeneous?
Like protein sample with many proteins inside, or these kind of things.
That would be super interesting to try. I mean, fundamentally, I don't see why not. You have to build the model. Those kind of models will take a bit more thought, because you need to be able to extrapolate reasonably well, or right? I mean, you generate different combinations of your base pairs and or your structure, and you have to have sufficient similarity so you can extrapolate to larger systems. But that's certainly it's a very interesting prospect. If I was in biophysics, I would have already done that.
All right. Okay, thank you very much. So I don't know if there's other questions. Well, no? Yes, Francisco, go ahead.
I have a bit of a curiosity more than a question. I mean, it's a bit naive also, but so basically you are learning the relationship between, let's say, the potential landscape of your molecular dynamics problem. Have you tried to assess if your neural networks learn something explainable, something that can be somehow related to some physical properties, some shape of the potential, but that's a bit a long shot. Do you know if the structure, the weights of the neural nets can inform you somehow of the system? It can give you a physical insight.
So interpretable machine learning is a super interesting aspect in general. For these kind of problems, okay, there's a lot to say here.
We also have the follow-up session. If you like, we can discuss it.
No. I'll try to keep it tight. I realize this is at the end of the day, so you people also would like to probably get home at some point. The short answer is they are not as easily interpretable. It's not just you cannot just plug another network on top of it and suddenly see, oh, this is how the interaction looks like. You can always take these models and just probe specifically what's going on, right? I mean, I can take my SiO2 or SiO bond and just stretch it, but it's not going to be that insightful. But there is something here that I want to show you, and that is, I think you see now the slide, because this was originally hidden. This is how the descriptor itself is built up, and so the descriptor is built up by having a bunch of basis functions, and these basis functions themselves are constructed from by adding up several different Chebyshev polynomials. This is how it works for the pairs, and then you can extend this to angular terms. In here, you have these coefficients, and these coefficients are trainable. So once we have them, we can fingerprint different structures, and this is how that looks like. So if I take silica, so I forgot to say that the descriptor has 44 components, and there are 9 two-body components, and the rest is three-body. And what I show you here in colors, just basically I go from -1 to +1, and so this barcode shows you what kind of structure you have. And so looking at this, here we have amorphous silica, we have cristobalite and tridymite and coesite and sticklewhite. So I realize I've got quartz for some reason. You notice that the first four are all very similar, but the fifth one is very different. And this is actually completely sensible in terms of the underlying structure. The first four are all situations where SiO4 tetrahedra are present. The stickerwhite is a high pressure polymorph where your oxygen goes from a twofold to a threefold coordination. And so the descriptor picks this up. And so at this point, this is a kind of interpretation. And once you have your descriptor, you can also freeze it, right? So we train this thing, and I forgot to say, I mean, typically for this model, we have 3,000 or so parameters, which is very, very small compared to other architectures. But now I have my 3,000 parameters, and I can reuse most of them and then train something on top of it. So we've done this, for instance, to predict electronic dielectric functions. Right, so I have already a model that knows how to differentiate between stickerwhite, coesite, etc. And then I build something on top of that. And so this is the closest I can go to explainability. Does that help?
Yes, very interesting indeed. Thank you.
All right. I don't know if there's other questions. If not, we can thank again Professor Erhart for the nice talk and the discussion afterwards, and also the other speakers, I guess. And then Francesco, if you want to take the lead again for the closing remarks.
Yeah, so thanks again also on my side to all the speakers. Very interesting session, I must say. And now we have a follow-up session in which, if you want, you can stay and we can have a discussion about the topics we just heard from the speakers.